Please welcome Desiree Plata, Associate Professor of Civil and Environmental Engineering, MIT.
Today, economic growth depends on carbon dioxide emissions. Prosperous nations emit 10 times as much carbon dioxide per person per year as less prosperous nations do. And historically, the only way we've moved between these lines is through geopolitical restructuring or enormous development. We can sit here today and entertain the fantasy that coal-based energy is going away, but I can tell you that that is not the reality. In India and China, coal is critical to the individual's access to be able to develop. It's critical to their access to energy. It's critical to their access to prosperity. In order to meet their energy needs, they're reliant on coal. And furthermore, coal supports an infrastructure like the train system in India, where the subsidies from coal transport discount the rate of passenger transportation. 5 million people are directly or indirectly employed by the coal industry, and another 23 million rely on that train infrastructure to get them to work each day. What happens when that goes away? And who decides? Because of this, nations are not decarbonizing their energy infrastructure, but instead doubling down on coal. And this is the inevitability that we are faced with. The Intergovernmental Panel on Climate Change projects that carbon dioxide emissions are going to stay high for the lifetime of everybody in this room. And in order for us to meet those 1.5 and 2 degrees centigrade targets, we not only have to revolutionize our energy systems, but also be drawing carbon dioxide equivalents out of the atmosphere. We have to do this on the order of 13 billion metric tons annually by 2050. Now that's the size of the coal industry, the natural gas industry, and the oil industry all combined. And they had 150 years to scale, and we've got to do it before this year's graduates get to their mid-career crises. Now there's 2 ways that coal impacts greenhouse gas emissions. The first and the biggest one are the CO2 emissions directly from the combustion of coal to generate electricity. The second is the release of methane, or CH4. This is a geologic methane source. When you open up the earth, it's released naturally. And it's an inevitability, again, that we must address. For every million molecules in the air in front of you, 2 of them are methane, and around 426 of them are CO2. Yet methane and carbon dioxide will warm the planet in equal proportion over the next 10 years. The other important distinctions that I want you to remember about these 2 greenhouse gases are that CO2 is long-lived and tends to be emitted in concentrated sources, whereas methane is short-lived and tends to be emitted in dilute fashion, even at these coal mines. Pound for pound from the point of release, carbon dioxide is a low and slow warmer. We could drop CO2 emissions to 0 today, and that would be nice, wouldn't it? But the climate doesn't feel it for 50 years. Methane, in contrast, does its damage early and then converts to CO2 in the atmosphere through natural processes. Now, if we could accelerate that conversion of methane to CO2, we would undercut methane's ability to warm the planet and change the rate of climate forcing that we experience in our lifetimes. Methane controls the rate of climate change over the next few decades. CO2 controls the absolute amount. One is a race, the other is a marathon. We need to manage both. I'm going to focus today on methane and tell you that the majority of methane emissions, over 80% of them, come from these low concentration streams. All of our traditional engineering approaches are designed for those concentrated streams. They're more economic. And I'm thankful that I'm not trained as a traditional engineer, but someone who tries to think differently about these problems. So thinking back to when I was a student in the MIT Woods Hole Oceanographic Joint Program in Oceanography, I was taught about microorganisms that live in deep ocean sediments that are able to make a living on dilute and diffuse methane in the presence of oxygen at atmospheric pressures and low temperatures. Now, these microorganisms almost universally rely on a protein that has a highly conserved crystal structure. This protein typically relies on earth-abundant metals. You're looking at copper atoms, those spheres in the middle of the structure shown here, in a nanoscopically tight pore space. That coaxes methane out of its configuration to turn into a less potent greenhouse gas. And these bacteria do this difficult to execute chemistry using these types of proteins, but we can't use them in the same ways. It would be wildly expensive for me to produce these proteins using today's technologies at the scales required. So we wanted to simulate this biochemistry with an abiotic process. If you go outside later today and scoop up a handful of dirt or dust, the chances are that you're going to be holding on to an aluminosilicate clay, or a zeolite is one type of those aluminosilicate clays. Those zeolites have that same nanoscopic pore spacing that I described earlier, and we can dope those with earth-abundant metals like copper and iron, the same magic ingredient used by the bacteria to perform that chemistry. And that gives us access to a sustainably derived, inexpensive catalyst. Now, when we first tried this chemistry at atmospheric conditions, we were surprised that we were able to destroy methane at concentrations just like the ones we're breathing right now, down to those 2 parts per millions. And it even works at enriched sources, like those in the depths of coal mines and coming from the mouths of cows in dairy barns. Now, the next thing that we had to do was think about how to get this abiotic, earth-abundant material into a filtration system that could interact with the ventilation systems that are present in coal mines and dairy barns. The flow rates in these environments are on the order of 1 million cubic feet a minute. That's an astronomically high flow rate. Imagine 10 tractor trailers moving by you in 5 seconds and having to get all the methane out in an instant. That's the challenge that's on the table. We wanted to go to these environments because just like you use methane in the natural gas to heat your home and it generates a little bit of heat, coal mines have enough methane to actually drive the process itself. So we have our ventilation almost for free, we have our heat almost for free. That's carbon abatement at a very low cost. But the challenge that you can imagine, blowing 1 million cubic feet a minute through a powdered catalyst, that's going to be pretty messy. So we've spent the last few years trying to structure this material into something that can tolerate those high flow rates. Here I'm showing catalyst pellets, and here I'm showing a zeolite monolith, a honeycomb structure very similar to what's found in the catalytic converter of a combustion engine vehicle. Now, the video that you're watching is a 3D printer developed by our friends at Desktop Metals, another MIT spinout. You've heard of 3D printing for plastics. You've heard of 3D printing for metals. This is 3D printing for ceramic materials. It's a really new innovation. And this video was actually taken at a BMW manufacturing facility where the scale of 3D printing of these ceramics is the size of your car engine. And that is critically needed in order to lower the cost of these materials and be able to produce them fast enough and at a scale that can impact the levels of planetary change that we'll experience in the next 20 years. We're really excited about this development, and we're driving hard to get it into the market by 2030. If we could do this at just half of the world's coal mines, it would instantaneously stop the accumulation of methane in the atmosphere. That would allow the Earth to catch breath and recover, and maybe even start moving in the direction that we need to go. In order to realize this vision, we founded a company called MoxAir. MoxAir is devoted to methane emissions reduction, not just in coal, but in other sectors. We can abate carbon for very low rates of $5 to $15 a ton CO2, 21 kilowatt hours as opposed to 2,100 kilowatt hours per ton CO2 equivalent by competing technologies. And it could potentially remove around 500 million gigatons annually in this application alone. And that's a $12.5 billion market if you can sell those carbon credits for a mere $25 a ton CO2. That would be transformative. That would be a carbon drawdown economy. If we could get this technology deployed to reduce just half of anthropogenic methane emissions, it would save 0.5 degree warming by 2100. That's 0.5 degree of the 1.5 discussed by governments all over the world today. And so one of my favorite things about being an MIT professor is that my students ask themselves, what brings me joy? What are my talents? How can I make the world a better place for other people? I want all of you to ask yourself those same questions today and imagine what you might be able to do to lift up societies, restore the climate, and generate a carbon drawdown economy. Thank you.